Hello everyone, this is Dr. Amy McCleney here, and I'm going to be going over the comparison of CFD multiphase modeling approaches for liquid-liquid separation. But before I do, if you have any questions or comments regarding this presentation, please feel free to contact me via email at any point in time. So this is the outline for this presentation. I'm first going to be going over some background information on computational fluid dynamics, or CFD, and then I'm going to be going over into some background information on multiphase flows and why they are difficult to actually simulate. And finally, I will be touching base on CFD modeling of separation technology, and finally showing you some examples of some liquid-liquid horizontal gravity separator simulations. And I do want to note this quote that I have here on the bottom of this page that was by George Box, who was a British statistician who is noted as one of those most brilliant minds of the 20th century. And he's quoted as saying, essentially all models are wrong, but some are useful. And what this means is that imitating what actually occurs in real life is challenging, and models aren't perfect, but some get kind of close, and we'll get into that a little bit more during this presentation. So why is CFD important? CFD stands for Computational Fluid Dynamics, and it is the analysis of fluid flows using numerical solution methods. Using CFD, you are able to analyze complex problems involving fluid-fluid, fluid-solid, or fluid-gas interaction. CFD analyses have a great potential to save time in the design process and therefore tend to be cheaper and faster compared to conventional testing. Additionally, it can aid with experimental testing or initial design phase, either through validation or a verification campaign. Additionally, in real-life experimental testing, you're able to only measure a limited amount of quantities at a single time, while during CFD analyses, all your desired quantities can be measured at once, and with a high resolution in both space and time, meaning you're able to obtain parameters that are not being able to be obtained via traditional experimental techniques. So here are some CFD applications we conduct here at SWRI. The first one being some oil and gas production and transport. We also look at pipeline accidental spill and leak assessment, as well as erosion of equipment and piping. We are also able to simulate environmental flows, as well as space vehicle propellant dynamics. We also look at medical device operation using CFD, as well as fluid processing. And finally, we are able to conduct fluid structure interaction simulations. So something that is always important with modeling in general is validation and verification, which kind of goes back into the statement that all models are wrong, but some are useful. In the case of erosion prediction, it is ideal to fully correlate models through the use of experimental validation, as what you're seeing on this slide here, where we developed our own erosion model in-house here at SWRI through impingement validation test using different variables. So again, it just kind of goes into this idea that you need to verify that your model is accurately producing what occurs in experimental testing or in real life, because you can create a lot of beautifully wrong things using CFD. So what exactly is multiphase flow? A multiphase flow is a fluid flow consisting of more than one phase component and can exist in many different forms. Multiphase flows are common in industry as well as in nature. Specifically for two-phase flows, you have classifications based on the state of the different phases, such as a gas-liquid mixture, which could be anything such as boiling water or ocean waves. You can also have a gas-solid mixture, such as aerosols. You can have a liquid-solid mixture. An example of that is slurry transport or soil erosion. You can also have an immiscible liquid-liquid mixture, which is items such as emulsion. And you can have a combination of all three of those items, so a gas-liquid-solid, which an example of that would be oil transportation. So multiphase flows can be characterized according to their inherent morphology. You can have a separated system, kind of like that first image that you were seeing on the screen, where both fluid phases are continuous throughout the domain, where there is a defined interface between the phases. An example of this would be a stratified flow or an annular flow in pipeline. You can also have a dispersed system, where you have one fluid phase is dispersed in a non-continuous isolated region within the other, usually more dominant phase. For an example, you can have gas bubbles within your continuous liquid phase. These bubbles can be large or small, or you can have liquid or solid droplets in a gas phase. So why is simulating multi-phase flows challenging? Basically, because there's multiple physics and interactions that are simultaneously occurring that is complex and difficult to simulate. So here's a list that you're seeing on the screen, and this is just a few. There's a lot that actually goes into it. So the first item there, well, you basically have more than one fluid or component that is involved. These flows are transient in nature. You also can have fluid properties or fluid separation that is occurring that is creating some sort of discontinuity. You can have complicated flows near interfaces or even near walls. You also have the interaction of small-scaled structures such as gas bubble interaction or particle-particle interaction, and there's some models that take into account all these different interactions. You also have a multi-phase flow, is multi-phase in both space and time, which I'll go over a little bit more in the next slide. There's also this addition of how we treat our dispersed phase interaction with the continuous phase, which leads to how the solver handles mass transfer as well as these phase changes. And finally, you have turbulence models. And turbulence is a cascade process. As turbulence decays, its kinetic energy transfers from larger eddies to smaller eddies, which ultimately dissipate into heat through the action of molecular viscosity. Resolving the smallest eddies use a discrete mesh that is unrealistic due to the computational resources required that would be necessary. Instead, you have some models of the turbulent dissipative process that are employed. So there's two big approaches to turbulence models. You have a two-equation turbulence model, where you have your transport equations for your turbulent kinetic energy and energy dissipation rate are solved in both space and time. An example of this type of model is the standard K epsilon model, or your realizable K epsilon model. You also can have a stress transport equation turbulence models, which solves for the differential equations governing the evolution of tensor that represents turbulent stresses. An example of this type of model would be the Reynolds stress tensor. So besides this turbulence model, you also have multiple models that are involved that look into the drag, lift, heat transfer, some frictional stresses, collisions, kinetic theory, etc. So there's so much physics that has to be considered, and that's why it's difficult to capture multi-phase flow accurately. So I mentioned this on the previous slide, that multi-phase flows are multi-scale in nature. So you have to account for all the scaled or the cascade effect of the various flow physics. So you may be trying to simulate something that's on the system scale or the larger scales, which we look at free surface or large or medium-sized bubbles. You also have this mesoscale, which are your medium scale, which look at the coalescence or breakup processes of droplets or particles. And then you have the microscale, which are your small scales, where you have the motion or interaction of small particles. Again, these all just kind of add into the complexities of modeling multi-phase flow, because currently there's not really one model that can resolve all of these things. It actually takes the right combination of multiple models to accurately capture the physics you're trying to recreate. So there's different approaches to multi-phase modeling. The first one being you can have a fully resolved model, which is kind of like you're an ideal case, where you solve all the complete physics, where all spatial and temporal scales are resolved. This is the most complex type of model there is. You also have a Eulerian approach you can take, For this approach, modeling all phases are treated as continuous with the ability to interact with each other. Phase volume fractions of each species are assumed to be continuous in both space and time, summing to unity at each nodal point within the discretized domain. The Eulerian technique may be further divided into the volume of fluid approach, so VOF model, the mixture model, and the Eulerian model. And finally, the last approach is the Eulerian-Lagrangian approach. In this approach, the most prevalent fluid phase is considered as continuous and solved using the time-averaged Navier-Stokes equation. The dispersed phase is simulated as droplet particles tracked through the flow field based on Newton's second law. A large number of particles are generally required for the sake of accuracy, and the Eulerian-Lagrangian method is normally only recommended when the discrete phase represents 12% or less of the total volume fraction of the mixture. So if you have a secondary phase that is above 12%, this model is not the best approach for solving that multi-phase approach. However, the more fully resolved and more complex the modeling approach is, the more computational resources are needed. So for the fully resolved model, that's the most complex model, meaning it is more computationally expensive to use that model. So how do we decide which approach is best to use for our modeling our multi-phase? For dispersed systems, you can either use a Eulerian-Eulerian approach or Eulerian-Lagrangian. For Eulerian-Lagrangian, is mainly for particle tracking with discrete phases that are less than 12%, as we discussed from the previous slide. Or with Eulerian-Eulerian model, you have the mixture model or a Eulerian model you can use. For the mixture model, the phases are considered as interpenetrating continua. A single set of momentum, continuity, and energy equations are solved for the mixture as a whole, while the volume fractions and relative velocities are solved independently for different phases. And finally, you have Eulerian-Eulerian model, which requires separate equations of momentum, continuity, and energy for each phase, with interphase exchange coefficients required to account for the interaction between the phases. Now, if you're trying to model separated systems, you can only take a Eulerian-Eulerian approach, such as with the volume fluid method. So VOF, or volume of fluid model, is a surface tracking scheme used primarily for instances where interfaces between phases remain sharp. So what goes into the design of gravity separators? The oil and gas industry uses gravity separators as the primary means to separate the fluid components of wellbore streams for either storage or further processing. These streams can include mixtures of crude oil, water, and/or gas. Since a multiphase separator is generally the first piece of equipment encountered by the multiphase fluid leaving the field, its efficiency affects the capacity of the entire facility and can present a bottleneck to downstream processing equipment. Proper design of separation equipment is essential to maintain the mechanical integrity of downstream equipment and to prevent operational issues that can be very costly to resolve. Repair, retrofit, and replacement of separation equipment are not always feasible and can easily exceed initial procurement and installation cost. While separators are used in all sectors, reliable separation is especially important to the economic viability of remote location resources in difficult applications, such as heavy oil, produced water, and sand disposal. Separators are composed of large vessels with complex internals to promote coalescence of liquid droplets and eliminate mist from gas. Design of multiphase separators is a non-trivial task, requiring complex separation physics and knowledge of fluid properties, flow rates, and inlet mixing conditions. Proper sizing has historically been strongly dependent on data collected at field-like conditions. However, most of the available data, design guidelines, and prediction models are based on air-water analyses at atmospheric conditions. This can be problematic since the performance of separation systems with hydrocarbon fluids and at elevated pressures is often significantly different, resulting either an overly conservative design or undersized equipment. Compounding the difficulty is the fact that floating platforms must also deal with severe weight and footprint limitations for separators, in addition to allowing for unavoidable wave motion expected at sea, which has mixing effect that tends to decrease separation efficiency. Separator designs can employ analysis from bottle shake tests, experimental studies, and modeling. Shake tests involve fluids with realistic well properties put into a small container, shaken or agitated for a certain time, and then timed for gravity separation. These tests tend to be a little bit crude, but can give an indication of the needed residence time for separator sizing. Experimental studies, on the other hand, can be quite accurate if realistic fluids, flow rates, and internals are used for testing. However, such tests are generally quite expensive, with the cost being especially prohibitive in the prototyping phase of design. Finally, computational numerical models with varying degrees of complexity can be used to aid in the design of separators. So, separator modeling using CFD represents an economical option for design, but caution must be used in the setup interpretation of data. There are many examples out there in literature of poor agreement between simulation results using particular models and experimental field data. Because there are a lot of different combination of models that can be chosen, kind of mentioned them in the previous slide, that look at your drag force, droplet breakup coalescence, foaming, multiphase mixing, and emulsification. The best results in terms of complexity and perceived accuracy has not been identified. Another way researchers have tried to minimize computational resources for separator modeling is by taking advantage of symmetry in the geometry to simulate only a portion of the domain, treating the flow basically like a plug bow. But researcher has found little success with this approach. Full 3D simulation significantly increases your simulation times, though, compared to cases taking advantage of perceived symmetry. Additionally, some authors do not even resolve the entire internal geometry of the separator, choosing instead to utilize porous medium models to represent certain internals, such as perforated plate baffles, in order to reduce mesh requirements. A lot of the studies that are out there also do not include the steps for conducting this analysis, where a majority of the studies only include overall CFD methodologies that were used. Additionally, there's multiple CFD software out there that claim to accurately simulate these types of flows. While the submodels available between these packages are more or less similar, it is desirable to independently verify whether the solution algorithms are significantly faster in either one, since multiple vendors claim proprietary improvements to increase solution speed. This can be important to the overall modeling technique researchers use, since computational solution time is the main driver for a decision to use simpler submodels to represent various physical phenomena. So I'm about to go into some of the CFD work that we accomplished here at SWIRI looking at liquid-liquid separation for horizontal gravity separators. And this was conducted in both ANSYS Fluent and Siemens Star CCM+. So this was mainly a parametric study to determine what was the best modeling approach in each software package, not necessarily which software performed better than the other. For this study, we had experimental data that we could use to validate our modeling approach. And we compared different drag and turbulence models that covered a broad range of flow rates, water cuts, and oil viscosities. So this is the horizontal gravity separator that we used for this CFD simulations. This is a solid three-dimensional model of the horizontal separator that was generated in SOLIDWORKS. This separator has a length to diameter ratio of approximately 5. So how this works is an oil-water mixture first enters the separator through a vane diffuser, which breaks up the inlet fluid stream momentum and distributes the flow across the vessel. The combined fluids then encounter 3 successive baffle plates, which act as flow conditioners. The fluid mixture then enters the gravity separation portion of the horizontal vessel, where the creation and fallout of large liquid droplets occur, and the fluids separate into their respective bulk phases. The then separated fluid phase encounter a weir plate, where ideally pure water flows through the water outlet and pure oil flows over the weir plate and out of the oil outlet. So this is the domain discretization, which is a fancy word for meshing. The fluid volume inside the solid model geometry was initially extracted for domain discretization. A mesh of this fluid volume was created using a polyhedral meshing capabilities in the Fluent solver. So that is the bottom image that you are seeing on the screen. The mesh for star CCM solver was created with its built-in meshing capability. And that is the top image that you are seeing on the screen. So the final mesh resulted in a cell count of 1.8 million polyhedral elements in Fluent and 3.4 million cut cell elements in star CCM. So for these simulations, we used the full 3D geometry, including the internals, meaning we did not utilize symmetry or use porous medium models for the baffles. We also did a grid refinement study, so a mesh refinement study, and those studies only showed a small change, less than 2% in the overall separator efficiency, with doubling of the mesh size, meaning the doubled grid resolutions had the double grid resolution did not offer anything in terms of increasing or getting a better result, but did significantly have a higher computational cost, meaning they took a little bit longer to run, so we decided to keep the geometry meshes that we have here as being the ones we use throughout the entire parametric studies. So simulations were conducted for 11 combinations of 3 different flow rates, water cuts, and 3 viscosities. You can see the range of experimental efficiencies that were used for comparison for the simulations in that last column there in the table, where the highest efficiency there is around 98%, while the lowest being 16%. So there's quite a bit of range of experimental efficiencies that we were trying to mimic. The overall water separation efficiency was used as the main metric in comparing the simulations to each other as well as to the experimental measurements. The water separation efficiency is based on the water concentration at the oil outlet line, as described in this equation here, noted as eta being the main symbol. The simulations conducted in Fluent were initially run using both a steady state and transient solution with the same modeling approach as to check on the solution sensitivity to an implicit transient versus implicit steady state convergence algorithm. Both cases resulted in similar separation efficiencies. However, the computational time decreased by half when the simulation was run in the steady state when compared to the transient solution. Therefore, domain discretization using 6 parallel processors were carried out using a steady state approach in Fluent in order to reduce the total solution time. Conversely, based on the difficulty in reliably obtaining a converged solution using a steady state approach in star CCM for the prescribed modeling approach, it was necessary to carry out these case studies using a transient solution methodology. Transient solutions with star CCM plus were run sufficiently long, such as the physical time for droplets to settle from the top to the bottom of the separator was reached. Note that the droplet settling time due to buoyancy forces is approximated using the V sub t equation that is noted on the screen. Simulation case 0 in that table was used to perform sensitivity studies to select the most appropriate mesh resolution, droplet distribution model, turbulence model, and droplet drag model. So these were the modeling approaches that we chose for both solvers. Based on the best practices for liquid-liquid separator modeling and baseline simulations in both Fluent and star CCM, we chose to use the Eulerian multiphase model, where oil was treated as the primary continuous phase. The dispersed water droplet sizes varied between test conditions and were defined in the software to be uniformly distributed at the separator inlet. The baseline cases used monodispersed water droplets, which were uniformly injected at the separator inlet, as I just mentioned, but the droplet diameter was based on the experimental solder mean droplet diameter sizes measured near the inlet of the test separator during the experimental testing. Simulations were also performed with multi-dispersed droplets using the population balance method, or PBM, in Fluent, and the S-gamma model in STAR-CCM+. The respective models provided a slight improvement in agreement of the simulation results, but only by 1 to 3%. However, the computational time increased significantly. Since adding a droplet size distribution did not significantly improve the overall simulation results within a reasonable computational cost, monodispersed constant size water droplets were used for all simulations. Initially, a sensitivity study on the different turbulence models was undertaken. The realizable K epsilon, standard K epsilon, and K omega turbulence models were considered here. The simulation results from all three turbulence models were in close agreement and had similar computational cost. Based on the best practices for multiphase modeling with each software package and the accuracy of the results during the baseline simulations, it was decided to use the realizable K epsilon mixture model in Fluent using standard wall functions and use the standard K epsilon model for all the simulations conducted in STAR-CCM. A sensitivity study on the different drag models available in Fluent and STAR-CCM was also performed. The table listed on the slide lists all the models that were used for these simulations in the respective software package. In Fluent, the Morsi-Alexander drag model, in combination with factors that incorporate surface tension and virtual mass effects, performed the best of all the four choices. In this case, the overall separation efficiency was within 1.5% of the measured experimental value. In STAR-CCM+, the Inverja-Rush-Issa drag model performed the best of all three choices. The separation efficiency was within 2% of the measured value. It is noted that this drag model is promoted in STAR-CCM as having a built-in pseudo-emulsion model based on empirical correlations from experiments. So this is the solution initialization, and it was conducted the same in both STAR-CCM and Fluent. So the simulations were generally initialized with two fluid phases completely separated within the separated vessel, as shown within these images here. The water height, which is the blue color, was based on the experimentally observed water level for each test condition. This idealized initialization was found to dramatically decrease the computational time required to converge on a steady state condition. A small amount of back pressure at the water outlet was also required to simulate the experimental downstream flow restriction presented by a control valve in the test setup. The back pressure magnitude in the simulated water outlet was specified so that the water level height inside the separator was equal to that experienced during the experimental testing. The numbers that you are seeing in the images themselves, 1 through 6, indicate the locations where oil and water concentrations from the simulations were compared to the measured experimental values within the simulation results. So there were 4 inside the separator itself, there was 1 at the water outlet, and then finally the 1 at the oil outlet. And at the oil outlet, the experimental separation efficiency was mainly the main driving factor used for a comparison. So these are the simulation results. The graph that you're seeing there is for location 6, which is the separation efficiency at the oil outlet. So this graph shows the percent difference between the experimental and simulation results, where a value of 0 means the simulation result matched the experimental results exactly. The simulation results indicate that Fluent was able to predict separation efficiencies within 8%, while STAR-CCM Plus was within 7% of experimental results for all test conditions. For oil and water concentrations inside the separator, you can see that table that is located on the slide. The largest was a 23% difference was seen for case 10 at location 2 for STAR-CCM Plus. Looking at the graph overall though, fluid tended to underpredict the experimental separation efficiency, while STAR-CCM Plus tended to overpredict the result. However, both tended to perform reasonably well, and were able to predict a separation efficiency within plus or minus 10%. And that was because we initially did all these different sensitivity studies to choose the best modeling, multi-phase modeling approach, as well as the best submodels that would provide us the most accurate result. So again, the table below the graph shows the largest deviation in oil and water concentrations for all the different locations between these two softwares. As you can see, Fluent had the largest deviation in oil-water concentrations at location 3 for case 2, which was the case that had a low viscosity, a high flow rate, and a 20% water cut. So we will look at the oil volume fractions here shortly in the next couple slides, what that looked like. Again, STAR-CCM struggled a bit with case 10, which had one of the lower separation efficiencies of being the 16% value. We believe this deviation occurred by not being able to effectively capture the physics of the interface between the oil and water mixture, as the experimental case was observed to have a good amount of emulsion present in the separator itself. So let's now look at the oil volume fractions. So these are the results for the test separator for case 2, which Fluent struggled with a little bit. So the top graph being from STAR-CCM and the Fluent being the bottom graph there. So what you're seeing here is both oil and water phases can be seen relatively well mixed at the inlet of the separator in this figure. Once the fluid exits the inlet device, the dispersion layers of the oil-water can be seen separating into the pure bulk fluid phases, where the concentration profiles remain relatively constant until reaching the solid weir plate. A thin fluid mixture layer is observed, and it maintains a relatively constant thickness past the last perforated plate. Now this is for case 10, which was the case that STAR-CCM had the hardest time getting the correct answer for. So for case 10, you can see a huge difference between the results from the previous slide. The dispersion fluid layer thickness is much larger. The mixture layer thickness decreases as it first goes through the first two baffles, and then it increases again after the third baffle, where a portion of the water is actually flowing over the weir plate. Although the oil volume fractions inside the test separator look relatively similar in both CFD solvers, the overall separation efficiency between the two software packages were significantly different. So since case 10, we had a hard time with simulating that in STAR-CCM, mainly due to the possibility of being able to accurately capture the physics of the emulsion we saw present during the experimental testing. We went ahead and modified the drag model in Fluent to account for emulsion effects. The drag model selected was the inversion Rush-Issa drag model, which was inherently built in STAR-CCM. This model is, however, not a default option in the Fluent software, and was therefore integrated as a UDF multiplier on the Schiller-Newman drag law. The reason we chose this model to simulate in Fluent is that because of the fact that this drag model is promoted in STAR-CCM+, is having a built-in pseudo-emulsion based on empirical correlations from experiments. Once we did this, we saw an improvement in oil-water concentrations in Fluent using this drag model compared to STAR-CCM, the largest being a 15% improvement in accuracy between the two solvers. So this exercise just shows you that by tweaking one item, it can dramatically change the results, and that you need the right combination of models to give you the correct physics. So subsequent investigations to what I showed you here during this presentation explored more of the emulsion modeling approaches, since we noticed that the solver struggled a bit with cases that had more emulsion present during the experimental testing. So an emulsion is a mixture of two immiscible fluids, where one fluid is dispersed in the form of droplets in the other continuous phase. Crude oil and water emulsions are viscoelastic fluids that have a complex rheology. sometimes in which the viscosity of the emulsion is much higher than the oil itself. Some emulsions have very low solubility, where the solution mixture will form a thick film that surrounds the water droplets, kind of like the image that you are seeing on the screen here. This film inhibits droplets from contacting, thus preventing droplet coalescence, which prevents the separation of the two fluids into their respective bulk phases. Emulsion modeling can be broken down into 3 different high-level groups. There are models based on fundamental rheological modulus properties of the material. This group incorporates physics based on expressions for interactions between the continuous phase and the suspended phase. An example of this model will be such as the one we just looked at, which was the Inversa-Rusch-Issa drag model. That falls into this first group. The second group combines the rheological properties of the individual liquids into a relationship describing the viscosity mixture. These models require measurements of the viscosity of the base fluids, but the effects of the liquid-liquid interactions on the overall mixture viscosity are accounted for in the expressions that combine the individual viscosity values. And this approach is actually the most commonly used approach for emulsion modeling. And finally, you have this third group, which uses the direct measurements of the stress-strain properties of the mixture itself in the overall mixture viscosity of the model. So these are subsequent investigations that we didn't go into a whole lot during this presentation, but were investigated during this simulation effort. So in conclusion, I went over some background information on CFD and why it's important, and some background information on multiphase flows and why modeling multiphase flows is extremely complex. I then went into some information on design of separation technology and some CFD modeling approaches for separation technology, and then showed you some examples of liquid-liquid horizontal gravity separator simulations that we conducted here at SWIRI. Some high-level takeaways is knowing that knowledge of correct modeling approach was thus far limited in current literature, so this study was aimed at trying to provide or look at what are the best submodels that are out there for accurately simulating these types of flows. And we found that with our studies that CFD can be used as a capability to evaluate new separator designs, but you have to be cautious of what models that you use to accurately simulate the flows. Subsequent investigations looked at exploring different emulsion rheology models. And finally, we believe that both Fluid and STAR CCM Plus provided modeling capabilities for multi-phase liquid-liquid separation, so both perform very, very well within plus or minus 10% of our experimental data. So in case you were wondering about the experimental testing that was used for validation, you can find more information as described in these 2 OTC manuscripts that are on the screen here. Again, thank you again for listening, and if you do have any questions or comments, please feel free to reach out to me via email at any point in time.